12th session of this FDP will be taken by Professor Rakesh Maurya on the topic of integrated electric vehicle charging with multifunctional features. Professor Rakesh Maurya is an associate professor in the Department of Electrical Engineering at Sardar Vallabhbhai National Institute of Technology, Surat. He earned his BTech from KNIT Sultanpur and his MTech and PhD from IIT Roorkee. His research focuses on power electronics, switch mode power converter, power quality, and electrical drives with 50 plus publication and over 1200 citation. He has made a significant contribution to the field. He has received multiple awards including GATE QIP scholarship. Please welcome Professor Rakesh Maurya. Over to you, sir.
Thank you. Thank you. Uh, Let me start. First of all, am I audible to all? Anyone can respond?
Yes, sir. Yes,
Yes,
sir.
sir, it is audible.
So first
PPT is
of all,
also.
thanks UT Gorakhpur for giving me opportunity to interact with uh, the peer researchers and students. So I'll be going to share some of my experience in the area of integrated onboard electric vehicle battery chargers. And this is the work being carried out over the last uh, 4 to 5 years with my research team. So with these are the small group of research which I started in 2014, and with some small funding from the funding agency, and then the final outcome in terms of peer publications. My key research area includes the control algorithm for power filter technology, power converters for EV and plug-in electric vehicle charging, hybrid converters for nanogrid applications, and lastly, the multi-phase induction motor drives and its applications. Apart from this, where I am also involved in mentoring one of the startup in Gujarat, that is a smart charging solutions. And nowadays it is a very popular, and it's catering need of various researchers, industry, and other allied services. Today I'll be going to talk much about uh, uh, as you the charges on the output charger and there is a so main charger is on board. How we can get it to make the output now.
Sorry to interrupt you, but your voice is not audible, sir.
Okay, okay. Still, am I audible?
Yes, sir.
I'm audible. Yes. Am I audible? Hello. Now I'm audible?
Yes, sir. Yes, sir.
Okay. So, am I audible now? Yes?
Yes, sir.
Okay, thank you. So, as it is the last, probably it is the last day of your STTP short-term training program. So, I'll not going to talk about the importance of electric vehicle, challenges of electric vehicle, because you are well aware of that. Okay. So, if you see the range of vehicle available in our country, we have a very wide range of application, and we are catering the need of almost all consumers, all customers around us. These are the future. Now, coming to the classification of the charger, as I said, on-board and off-board chargers. So onboard chargers are basically, these are the classified based on the location of the charger. If the chargers are placed in car itself, in vehicle itself, I can term as onboard charger. Otherwise, it will be off-board chargers. So now location. So if you just look at the constraint, for example, if the charger is located within the car, then obviously there is a certain constraint of power rating, their size of the charger, weight of the charger. So usually the onboard chargers are designed for a low rating. Let's Depending upon the power level, for example, we have a level 1, level 2, level 3 chargers, and the level 1 charger is designed for up to the 2 kilowatt chargers. Similarly, the level 2 charger, it may be on board, sometimes it may be off board also, and they can be designed to charge the vehicle, EV vehicle battery up to 20 kilowatt charging. Okay. And the level 3 is a truly off-board charger, which is derived from the three-phase supply and going to charge the vehicle, and it can be pump power up to 100 kilowatt capacity. So these are the few, and if you see, if you are going to design larger power rating of the charger, it can charge your electric vehicle battery with a very faster time. For example, if you have a level 3 charger and you are going to charge the vehicle, it can charge within 30 minutes, even lesser. So the charging power rating is directly proportional to the time, indirectly proportional to the time. More the power rating you design, it will charge the vehicle battery faster. Now, if you just look at this schematic, where the EV pack, normally we have in battery, we have a electric EV battery pack, which is to be charged directly through the AC plug. It means in between, within the car, we have an onboard charger. We have an onboard charger. So like this, here we have an onboard charger, and this onboard charger is through AC supply, we are going to convert into DC through existing onboard charger. And if we are plugging directly to battery, then we require it should be through the offboard charger. So here the DC charger, it is normally offboard, so that can be located outside the vehicle, whereas the onboard within the car we have a onboard charger, so which can be plugged through AC supply, and then it will going to charge the battery. So now here our focus is more about the onboard vehicle, onboard chargers. So it can be classified based on their power rating. So it can be derived from a single phase supply So we can call it single phase onboard charger. If you require to more power for charging a high size of the vehicle, like four-wheeler, buses, then you can go for the three-phase chargers. Then in onboard charge, single phase as well as three phase, we have isolated and non-isolated topologies. Then we have a unidirectional and bidirectional charger. When you charge electric vehicle battery through the supply mains, so the flow of power will decide whether you are going to charge, means you are going to charge your vehicle. For example, you are going to charge your battery, then the flow of power will be from grid to vehicle. So we normally call it G to V, and that is it is charged through unidirectional charger. But there are charger which is available which can flow the power in either direction. For example, bidirectional charger, where you can charge your vehicle battery through the grid. You can charge your vehicle through the another vehicle. So we normally, and we call it V to V, vehicle to vehicle, or grid to vehicle. Or there are add-on feature to it where the battery can supply power to grid. It can supply power to load. It can supply power to home. So all kind of multi-functionality you can include in the charger. So for that we required bidirectional charger. It is for higher rating as well as for three-phase category as well as the single-phase category. In both the cases it is available. Now there is a class of charger like we call it conductive and inductive. Conductive here where you required electrical connection between the charger and your supply socket. Inductive, it is through wireless. So in top of all, we have an integrated charger which facilitate many features as compared to the other chargers. So now I will be focused more about the integrated onboard chargers. So if you just look at some of the things where the rating of the charger is very, very important, because if you see, if you increase the rating like 3.7 kilowatt charger is a very common in vehicles applications, particularly for four-wheel. In most of the cases, it is 3.7 kilowatt, and some specific case it is a 7 kilowatt onboard chargers are available. In some European country as well as the US, 6.6 chargers are also available as a onboard chargers capacity. These are the power rating of the charger, and then some of the plug-in electric vehicle, which is most common, most popular. We have a 3.3/3.7 kilowatt chargers which is available. So in total, I can summarize here 3.7 kilowatt chargers are very common in electric vehicle. It means when you charge your vehicle, either two-wheeler or four-wheeler, particularly four-wheeler, whatever capacity of the battery, but you can allow current to flow, you can allow power to pump to the vehicle at the rate of 3.7 kilowatt capacity. So so what is the issues related to this? If you increase the size of the power rating of the charger, onboard charger, so it is going to add weight to the vehicle, and apart from this, you must possess the quality of high efficiency, high power density, etc. So again, I have a sum of vehicle model existing which is running, and their capacity of onboard chargers. So you can just go through serial number 1, 2, where the onboard charger capacity is of a 3 kilowatt charger like this, a 3.7 kilowatt charger. For this vehicle, let's say for the first vehicle I'm talking about, Here the motor rating is 30 kilowatt. It is powered through the single phase supply, one phase to 20 volt AC supply, and the charger capacity of 3.7. Similarly, if you go ahead, see the serial number 8, which is very popular nowadays. So we have a 7 kilowatt, 3.7 kilowatt and 7.2 kilowatt are the chargers, onboard chargers rating available in the market. If you see the Tesla model, where the onboard charger is rated up to 11.5 kilowatt, and the motor rating of the vehicle, which is used for driving in the Tesla model, it is varying around 300 kilowatt to 400 kilowatt. This is the data related to the four-wheel system. Now, similarly, some other case. So what I want to conclude here, the most of the onboard chargers are of 3.7 kilowatt capacity, whereas it is battery capacity. If you look at the battery capacity, it is for any case, let's say this one, the serial number 12, the battery capacity is 35 kilowatt hours and the voltage rating may be 22 volt to 144 volt. So you have to pump the power with a maximum capacity of 3.7 kilowatt through the charger to charge 35 kilowatt hour battery at the rate of voltage around 72 volt or 140 volt. So these are the data used to specify the study during our simulation or even hardware experimentation work. So even if you see the Tata Tiago, its battery capacity is of 16 kilowatt hour and the battery voltage is of 72 volt, and on-board charger is of 3.7 kilowatt, motor capacity of 30 kilowatt, which is operated through single phase to 30 volt supply. So why onboard charger is inbuilt in the vehicle? Can anybody respond? Because we need a bidirectional here a little bit. So can anybody tell why the onboard charger is required? Yes, please. Hello. Anyone? Why onboard charger is required? Yes, please. Anyone? I'm not receiving any response. I don't know whether people are there for the sake.
Version of AC power supply into DC, you need onboard chargers.
Yes, but why it is on board? Why it is why not it is at off board? The reason being, suppose whenever if your charger is inbuilt in your car, then you can easily plug into the place where the sockets are available. For example, you can easily charge your vehicle at your home itself. You need not require a separate charging port, charging unit to charge your vehicle. So onboard charger enables EV users to charge their vehicle from the domestic AC wall outlet. Even the cost to charge your EV at public charging stations, for example, you are going in shopping mall and you are going to charge your vehicle, obviously their rate will be commercial rate. But if you charge your vehicle at your home, their rate will be domestic rate. So this way it is very costly. So in few stations are free, but other stations are much costly. So even a onboard charger facilitate charging relatively as compared to the off-board charging. Okay, then So it is a universal reason why the manufacturer permits onboard charger in electric vehicle. Okay. So this part I have already discussed. What is the rating of onboard charger? It is near about 3.7 kilowatt, and onboard charger is obviously it is more than that. So now coming to the vehicle structure, let me come to the vehicle structure. So if you see this schematic diagram, where we have left side two wheel and right side we have a two wheel. So here we have a wheel 1, let me call wheel 2, this is wheel 3 and wheel 4. So if you see the structure, in normal case, this is the battery pack, which supply power to electric vehicle and during running condition, and whenever the battery is drained, it is to be charged. Then it requires a DC supply. So for that we have a inbuilt here we have an onboard charger which is placed in the vehicle itself, and then there is you can plug in this vehicle's supply, it means onboard charger socket to power grid, any grid, a single phase supply or 3-phase supply depending upon your availability of the connection port. So here you can plug in. So first instant is you have to convert power from AC to DC, and then this DC may not be suitable to charge your battery pack. So you required one more DC. So in total, you required AC to DC plus DC to DC conversion to charge your electric EV battery. Okay. So this is just a schematic diagram, which the purpose is just to introduce your schematic diagram here. Now let us look at the more simplified way, same in structure with more simplified way. When your car is running on the road, then the flow of energy from the battery to your motor, and motor is used to drive this wheel. It means your battery power is going through the bidirectional DC to DC converter, and then in DC to AC converter, which is normally called as an inverter. An inverter supply is connected to motor. It may be any motor which is competitive in today's EV market. So here I am just putting the general case where the flow is from battery to electric motor to drive the car. But when your battery is drained, then we expect that the power should charge your battery in the reverse direction. So what we are trying to do now, it means when the machine is running on the road, vehicle is running on the road, our motor is, let's say the motor rating, if you see the specifications for, let's say the Tesla motor, its motor capacity is of 3 kilowatt hour. 3 kilowatt motor is there, and obviously to drive this 3 kilowatt motor, you required inverter capacity of the same rating, almost higher than this rating. Then bidirectional DC to DC converter devices rating are also of the similar to control the flow of power. So it means the rating of these converters, either bidirectional DC to DC converter or inverter, are very, very high as compared to motor. If you see the parallelly here, it means here the bidirectional power rating is very high, inverter rating is very, very high, motor winding is designed for carrying high rating current. But this onboard charger which was located in the vehicle, it is of 3.7 kilowatts. So their current rating and power rating is a little lesser. So then here, if you want to increase the rating of the charger, then why not we utilize the infrastructure available during the vehicle operation? Because once the vehicle is stopped, suppose battery is drained, then obviously the vehicle will be stopped, and all the bidirectional DC to DC converter or inverter which is used to drive the vehicle is now idle. So now in integrated charger, we are going to utilize the vehicle motor windings, which is designed, which is already having high current rating capacity, inverters, which is there, even DC to DC converter, which is already if a high rating is available. So we can utilize the same infrastructure to charge the vehicle. Okay. So this is the simple schematic diagram. Suppose this battery is the battery pack. During motoring operation, the power flow is from battery to motor, and this motor is used to drive your wheels. I hope this diagram is okay for everyone. Is it visible now? Yes, please. So during propulsion
yes, sir,
mode,
it is visible.
Yes. So this is during propulsion mode, the battery power supplies the power to AC motor, and AC motor is used to drive the vehicle. Now, what this is a schematic diagram. Obviously, in between you required DC to DC converter also here, DC to DC converter also here. Okay. So, but this is the general schematic diagram. So when your battery is drained and it is expected to be charged, then why not we make some alteration? And what is the alteration? Let me see. Now I'm going to add. Here the motor neutral winding is available, and let's say the DC link capacitor. I have two series capacitor. So midpoint I am tracking here. So if I have single phase supply between the neutral of the battery to the midpoint of your DC link, this midpoint, let it call it O. So this can be utilized. I can pumping power. Let's say I'm putting single phase AC supply, and which is going through this motor winding, which is a very high rate. It can carry very high current. Then this inverter is of different, is also designed for high rating, because during motoring mode it has to design to meet the requirement of low torque, speed, and running conditions. So this inverter rating is also high, and obviously in between we have a DC to DC converter, so their rating is also high. So we can use the same infrastructure to charge your battery. But here the connection of motor is supply is from the motor side. I hope people have understood the concept. Yes or no? Now, so let's look at this particular same thing. Now I'm projecting for my situation, which we did in our laboratory. So we have a four-wheel drive. We have a four-wheel drive system, integrated EV charger for four-wheel drive system. The four-wheel drive system means I have taken example of a vehicle. Let me take a very small example, and then we will move to this particular point. Let me take one more example. Let us take this particular situation. I hope this vehicle, this is available. Yes, sir. Hello. Is it available? Yes, please. Anyone, please respond.
Yes, sir. Visible and audible.
Okay. So now if you look at the figure where I have taken two-wheeler, that in two-wheeler case, we have a motor. Let's say I am having Tesla motor. Let's say the induction motor is used to drive this two-wheel vehicle. Then there is a battery. Battery may be of 20 ampere hour and 72 volt or even 48 volt battery. and this induction motor is used to drive this two-wheel. Or parallelly, you can see this is a three-wheeler where the similar configuration is used to drive this two-wheel as well as the three-wheel during the motoring mode. But let's say I want to charge this battery. So when the battery is required charging, then this vehicle will be stopped and it should be plugged in. So what we are going to see, you can see here, we have during motoring mode, the battery is supply power to motor and motor is driving the wheel. Now when it is stopped, then this is the interconnection we are making. So what we are going to do, the first during motoring mode, we have a 3-leg inverter. So out of 3 leg, we are going to use 2 leg and 1 more leg for the DC to DC converter. So if you try to see here, let's say this is the motor winding both and the supply, and the first 2 leg we are incorporating to convert AC into DC. Okay, and now the second leg, the third leg is used to act as a whatever DC link voltage you are available at this particular point, that is going to charge your battery. So you can operate inverter, a third leg of this system as a DC to DC converter, and which can be operated either CC mode or CV mode depending upon the SOC of the battery. And so what we are going to do, we are not going to add anything extra in this vehicle, and we are utilizing the same infrastructure to charge the vehicle. Okay. Similarly, if you see the let's say the green, how this transition takes place from motoring to generating mode, during motoring as well as during charging mode. So in the motoring mode, green color is used when the vehicle is running on the road on the wheel on the road. So here, let's say the windings are connected in star and supply is disconnected. So during this case, the battery power supplies the induction motor. This is the induction motor, and it is running on the road. When it is required charging, then the orange color waveform is there. Here you have to disconnect supply, and this relay is now shifted to 2 point, and this third phase, the induction motor third winding is connected to 2. So in total, this entire structure, this entire structure is now converted into this particular structure, in which it is easily, I hope it is clear to everyone by looking to this diagram. First two leg of the inverter is act as a single phase full bridge PWM rectifier. I hope it is okay for everybody. If I am using this term, I expect everybody must know what is a single phase PWM rectifier. It will convert AC supply into DC supply, and during the conversion, it will also take care of the power quality issues, means it can operate at unity power factor operations. And obviously, suppose if you are applying to 230 volt single phase 50 hertz supply as the input, so here the voltage should be more than 400 volt. So let us I am taking 450 volt here, or even 400 volt DC link at this particular point. Now this third leg of the inverter is used to convert DC into DC. So if you have 72 volt DC and with 20 ampere hour capacity, so based on its SOC, you can operate this switch S3 and S5 so that it can carry current and charge your vehicle, this battery. So these all structures we have discussed, so I am not going to talk that much in detail. Let us come back to the 4-wheel drive system again. So now coming back to the four-wheel system. So in previous slide, I talked about the two-wheeler as well as three-wheeler. Now let's see the four-wheeler, where all the four will have a dedicated motor. Normally, we have a two-wheel drive system or four-wheel drive system or single-wheel drive system. So in this case, I am considering four-wheel drive system, where each wheel is connected through induction motor, and then means there are four induction motor, IM1, IM2, IM3 and IM4. It is coupled with mechanically coupled with this motor wheel, or it can be also termed as the hub, can be fitted in the wheel itself. Now there is a dedicated inverter topologies like VSC1, VSC2, similarly VSC3 and VSC4. So there are four inverter which is used to drive, which is supply power to induction motor during the motoring operation. Now there is a large battery pack. It is used to supply power to each inverter. So we have a DC link plus minus, and it is distributed in a such manner it can power to all inverter equally. So suppose if your inverter, your vehicle is of 300 kilowatt hour, 300 kilowatt is the motor rating for the Tesla four-wheel drive system. Let us talk about. It means now each motor is, this can be divided into four. So each motor is rated for, let's say, the 75 kilowatt. And accordingly, their inverter rating is also decided. So by this distribution, integrating means we are splitting the motor requirement by four, and then we are also reducing the current rating of the winding devices rating, etc. So now coming to the during motoring mode, the battery supplies power to each inverter, and based on the driving condition of the way, the road, the motor drives, and all the motor functions in synchronism. Means there is a one control and there is a sub control for controlling each inverter, each motors. Now coming to the charging mode, when the battery is drained and it is expected to be charged, then you need to halt the vehicle and your configuration need to be changed. So what I want here, I had to connect this neutral point of each motor. Let's say the front wheel drive, I'm talking about this front wheel, where the neutral point of each induction motor is connected to the supply, and the second line single phase supply I'm talking about, and the neutral point of the supply is connected to, means your supply has a one phase and one neutral point, na? So the phase is connected to, let's say, the neutral of each each motor, and the supply neutral is connected to midpoint of the DC link, like here capacitor it is connected. Okay, it means now we are converting with the help of IM1 and IM2 as well as VSC1 and VSC2. So these infrastructures are used to configure your converter in AC to DC converter. Its job is to convert power from AC to DC. And later on at the rear wheel, if you see the rear wheel where IM3 and IM4 is connected along with VSC3 and VSC4. So they are configured as a multi-phase DC to DC buck converter. So in which all the 6 leg is available along with the 6 winding of the motor, and their star point is connected and it is going to charge your vehicle. Okay, let us take one more configuration which will help us to see this one. In this case, again, as I said, the first this the four wheel, the rear wheel or front wheel of the vehicle in which the induction motor 1 and 2 are available. They are acting as a 3-phase, means there is a 2 unit of 3-phase PWM rectifier. Its job is to convert AC into DC. And obviously they are connected. There are 2 units connected in parallel at the DC side. So we can control the 2 independent unit as in interleave operation, so that the THD in supply is reduced further. So here we have a DC link available. It may be of 600, means 500 volt DC link. I can keep here as the DC link. And then the rear wheel configuration VSC3 and VSC4, along with machine 3 and machine 4, it can be connected as a depth converter. So all the possible configuration can be made with using this 6-leg inverter, as well as the 6 winding of the machine. We can design current rating of a higher value, because this motor and inverter available is of a higher rating. Now the control logic for front end converter, I'm just talking about the front side converter, AC to DC converter. It is a very popular, those who are well aware of means PFC converters. So in which PFC converter, let's say, as I said, the DC link of this is I am taking as a 500 volt DC link. So in order to that, let's say this 500 DC link is taken as a reference, and actual DC link is sensed. The error is generated, it is passed through the PI controller. So it will generate a signal, and then it will be constant and ripple free like this. With respect to time, it will be like this. Then you can sense the template of the sine wave, and then you can make the rectification or magnitude. Then you can get this rectified sine wave. You can multiply it. Here you will get the reference current for the supply, and then it can be compared with the actual current, and then it passes through the PI controllers, so it will generate the pulses. So this is the control block schematic diagram for either single phase PWM rectifier or 3-phase PWM rectifier. Obviously, if it is a 3-phase, then all the parameters will be change accordingly. But most general is, here we have a voltage control which compare the DC link voltage and reference voltage. Then the output of the voltage controller is multiplied with the template of supply, and then you will get the reference current. And actual reference current is compared, and it is passed through the PI controller for the generation of the pulses. So this is the basic for front end control we normally use. For this DC to DC converter, like rear wheel, you have 6 devices, means 6 leg and 6 winding. So you have to sense the battery voltage or battery current, and then accordingly you have to design the pulse. So if you want to operate converter in CC mode, you have to sense the battery current and keep the reference current of the battery as per the recommended charging practices. Like each battery is in specification, it is given recommended charging level like 0.1C, 0.2C or 0.5C. So accordingly you can set the reference, and you can allow battery to charge in CC mode through the dedicated circuit. And if you want higher charging current, then accordingly you can increase the C rate by 0.2, 0.5 or even 1C, depending upon the capacity of your charger and the recommended practice for your battery. So this is the control structure for your battery, which is battery charging DC to DC converters. So let us take a 2-wheel drive system. For example, I'm having two induction motor. One is going to drive the front wheel. This is the front wheel drive system. This is the front wheel, and this is the rear wheel. And so if both are connected during motoring mode, supply is not connected here, and this battery pack provide energy to this induction motor for driving front wheel as well as the back wheel through their respective VSC and motor. But when the battery drains, then it is to be charged. Then you have to keep it at halt, and you have to you have to plug in to the supply. Now here we have a single phase supply. It is, let's say, the front wheel drive first. So in the front wheel side, the neutral point of induction motor is now connected to, let's say, the P of the supply, phase of the supply, and the neutral point of the supply is connected to DC link point of a midpoint of this capacitor, that is DC link capacitor. So by doing this, we are putting single phase supply through through motor IM1 and VSC1. So we are converting AC into DC, and then this DC supply is now converted back to AC, DC to further DC, just by changing the switch point K1. This K1 is the switch point where if I put it at C connection, it means it is under charging mode, and during that supply is connected to the supply front end converter. And now if you put it at P, means propulsion mode, in which the supply is disconnected and motor is running on the road. So so as I discussed the control, the AC-DC converter, we have a different control. DC to DC converter, we have a control like CC charging mode as well as CV charging mode. So this can, and if you see this inverter, they have a bidirectional features. They have a bidirectional feature. Suppose you are at a place where nothing is supply is not available, then you can use the battery power to glow the surrounding. So this converter can be operated in bidirectional, and so this VSC1 can be operated in bidirectional way, and it can pump power to either grid or a local load. So you can use the local load for vehicle with the same infrastructure. So this have a potential. So this is a simple schematic diagram for two-wheel system, where front wheel is used as a AC to DC converter, configured as a single phase PWM rectifier, and DC to DC side, it is used to charge our vehicle under CC as well as the CV mode. Now same configuration for four-wheel drive system, where front wheel is configured, two induction motor, two VSC, they are connected and they are feeding power to this DC link. And hello, am I audible?
Yes, sir.
In between, if my voice is not there, please respond so that I can come back, because while presenting, I'm not able to see the screen. Okay?
Okay, sir.
So again, see, as I said, the front end converter, they are configured as a single phase PWM rectifier. But it is not the only way you can configure the single phase PWM rectifier or three phase PWM rectifier. You may use some other topology also to make the conversion from AC to DC. And this is the one example where the front wheel conversion, I am using one of the VSC. One of the VSC I am using as a AC/DC converter. And just a minute, I have a one call. Okay. So
Sir.
as I said,
So,
hello.
sorry to interrupt you, sir. Sir, but your screen is not visible, sir.
This screen is not visible.
Yes, sir, your screen is not visible. PPT.
Oh, let me check again because network issue may be the one of. Hello. Hello. Now screen is visible.
Yes, sir, but PPT is not. Yes, sir. Now it's
Now it is
visible.
visible. Okay. Okay.
Yes, sir.
Okay. So this is the one of the one of the topology where we are converting the front end converter. Means, as I said, we have a two wheel, and there to drive the two wheel we have a two induction motor, two VSC in four wheel operation. So one of the VSC, if you do not issue any pulse to the inverter, then it will simply act as a diode rectifier like this configuration. And the second VSC, which is already available in the machine side, you can rearrange, and there is no big task. There is a relay contractor system where you can easily flip the lower IGBTs, and you can make the connection like this connection, which is given in bottom figure where I am indicating. So this configuration is a simple, the front side diode VSC1 is acting as a diode bridge rectifier, three-phase diode bridge rectifier. And the VSC2 is now reconfigured in this topology. So entire circuit is the same as a VNR rectifier, three-phase VNR rectifier. Only the difference is I am supplying with the single phase supply. This is the concept where we are applying single phase supply. Can anybody ask a question? Why in all this integrated converter I am using single phase supply at the front side? If you see this topology or any subsequent topology, this topology, this topology, everywhere I am using single phase supply. So can anybody tell why I am using single phase supply to charge this vehicle? Anyone? Hello. Can anyone respond? Please respond.
Yes, sir.
So why I am using single phase supply? See, these are the induction motors winding. Okay. In induction motor, if you have this winding and it is connected in, let's say in this configuration, it is connected in star. This way I am supplying the current. Okay. So in each winding, the current flowing is the single phase, current is sine omega t. So there will be no rotating flux produced to rotate the machine. That is the only reason I'm using single phase supply at the front side to charge your vehicle. In order to, so that it will never generate the electromagnetic torque. Otherwise, it will start running. So this is the reason. Obviously, in some of the topology, you can use three-phase supply also, but in that case, you have to make some hardware reconfiguration so that the machine should not rotate while charging. So this is the only things which I wanted to highlight here. So here what you have seen, front end side, I have converted AC into DC, and then the purpose here I am taking Vienna rectifier, but they are supplied with the single phase supply to convert AC into DC. The control structure, as I said, if you go for the single phase or three phase, the topology is like this. We have a reference voltage of 500 volt, which is the DC link voltage. Actual DC link voltage is sense, and then it is through voltage controller we are generating the control voltage VK. Then unit template generation is this block. In hardware you can use PLL block to make a AC template, and you can multiply to get the reference current at this particular point. This reference current is now, if you have a three-phase supply, so it is to be taken care of each, means there is a motor winding, so each winding current you have to sense, and then it is, should be compared with the reference current, and then it passed through the error is passed through the current controller, PI controller, to generate the voltage switching pulses. So this is the control structure, control block for operating the front end converter. We can call it interleaved boost converter. Now this is the hardware setup which we have made in our laboratory, and you can see here in extremely left side we have a induction motor. Then through the auto transformer, we are giving the AC supply so that the reduced voltage is given. Then we have a STM controller, then diode rectifier, then VSC, and then the separate AC-DC converter we have done for the same topology. So let me run this program video so that you can understand. So this is the enlarged view of this experimental setup. Now you can see here the machine is running. Now we have a single phase induction motor, which the windings are reconfigured. Through auto transformer, we are feeding power, and then through VSC, inverter and card, at this point, we just as a demo point we have taken. So without any control, there was a 72 volt DC was generated. And now these are the STM32 controller. See that THD during without any control, its THD is 62%. Now the driver circuit is turned on, so the converter is now the THD is reduced to below 5%. The current is around 5 ampere from the AC side. See in the DSO the current waveform. The first three waveform is the individual current, phase current of the motor, and then this is the total supply current is the lower one. Finally, if you see the DC side, here the voltage is 110 volt, 108 volt. So this is the way we have tested our control is conversion from AC to DC. I hope this demonstration is visible to everyone. Yes or no? Hello?
Yes, sir.
Okay, I can rerun so that you can see this is the induction motor. AC supply is given through induction motor. Then the winding of induction motor is utilized. Then we have this VSC card which is configured as a Vienna rectifier. feeding to the DC link is 72 volt without any switching operation. Now this is the STM controller. Now 65% is the THD in source current without control. Now the driver is on and the operation takes place, and now it is PFC operation starts. The THD comes below 5%. Current rating of supply is around 4.6 ampere. See the DSO waveform, all currents are sinusoidal within winding. Machine current is also sinusoidal. And the voltage is 100 volt. 108 volt is the DC link voltage you have HE. So this is the first converter, AC to DC converter. This is the control STM32F407VG microcontroller used for realizing all the control complexity. This is some supply current. If you see the individual winding current, these are the, let's say, the phase A current, phase B current, phase C current, and this is the total supply current. Total supply current. Similarly, the DC side current and waveform are also shown. Now, again, this is the supply current, AC current and DC current. These waveforms are being shown. This is the THD supply voltage, small voltage I have applied. Then active power, reactive power is given. This is with respect to the supply. It is showing the supply condition. AC supply voltage, THD. Then current THD is 3.8, which is well within the IEEE regulations. Now, this is under steady state condition. Means in all the cases, winding current is having, let's say, the 1.6 ampere. 1.6 ampere is each winding current through the motor, whereas the total current is the 4.9 ampere. So total current THD is 3.8%, whereas the individual motor winding current is 4.5, 5 and 4.9% THD. The reason is the operation of each leg is interleaved manner, so that the total current is THD in total current is reduced significantly. Now this is the operation under dynamics load. Suppose if the supply changes or load changes, even in that condition also our topology works fine. Okay. Now here you have seen we have a requirement of different winding current, because you have to sense the phase A current, phase B current, phase C current of the motor. So you required sensor at the 3 stages. So what we have done, we have also tried to reduce the sensor requirement. So if instead of putting sensor in the winding current to sense the individual motor winding, I can put the sensor at this particular point. Right side figure you just see the one sensing point. So at this particular point, we can use a single sensor to do the entire operation. So that is called the sensor reduction technique in the integrated. So instead of only we are testing the operation, we are also putting the sensor reduction in this case. So this reduction is done, and it is working fine. Now coming to the DC to DC side, if you just look at this particular case, if you connect this particular point to the P point, let me connect this to this P point. Then this battery is now connected to each VSC, and each VSC is going to drive this motor 1. Let's say that this is the motor 3 and motor 4 of the VSC. But if you disconnect this P1 point, battery positive terminal, and if you put it to this P3 point, then push back, then it will join here. Then, and this DC link voltage you are getting from the front end converter, as I said, 500 volt DC you got from the front end converter. Then this DC is now through this, we have a 6 leg available here. One is a VSC3, this is VSC4. They are used to make 6 parallel 6-phase DC to DC converter, and that is going to charge your battery. So suppose if you are let's say you are using 72 volt 60 ampere hour battery. So each winding is allowed to carry 10 ampere current only, and it can charge the battery with the 1C rate also. Even since motor rating is more, you can take even 20 ampere each. You can reduce the this rating to 0.5C, means 2C rate. You can charge your battery to 2C rate. Only you have to increase the current rating. And since these motors are rated, they are designed to carry high current rating, so it can be easily installed. So what I wish to tell, by making integration in the vehicle, charging feature in the machine, you can easily allow more current to flow through the battery, and it can charge battery much quickly. So I can say the integrated chargers, they not only facilitate charging without adding extra component in the system, it is a faster charger, and it can be treated as a class 3 charger or even class 2 charger, which is much higher as compared to the conventional onboard charger. If you have a single phase, again in 3-phase winding, if you just look at here, here also you have this 3 motor windings. If you want to sense the, you need an individual current for the control purpose. Then instead of putting current at each winding, you can use the current sensor. You can use sensor at DC link at this particular point, and that will also facilitate the reduction of the sensor unit in this topology. So we are making integration for charging the electric vehicle. At the same time, we are reducing sensor requirements. So this is the EV charger for 4-wheel drive, in which the integration as well as the sensor reductions techniques are implemented. How the sensor reductions techniques works, that is I'm not going to talk much here. Okay. So again, the similar hardware for the 3-phase multi-phase winding, multi-phase DC to DC converter. The system is tested, and now you can see this motor winding. Their motor windings we have taken, and they are utilized to make it a 3-phase DC to DC converter. So you can see here, this supply we are used to make the DC supply, and that DC supply is going to charge the vehicle. This is the interleaved current motor winding. This is just for the DC supply, and this DC supply is operated through this particular inverter, 3-leg inverter. It is going to charge this 4 battery, 48 volt 7 ampere hour battery, and these are some sensors unit, LEM sensor, voltage current sensors are placed. We require regulated supply, so we require supply also. These are the motor winding. They are used to act as a filter inductor. So this is a demonstration for the second phase of the second block of the machine. These are some individual motor current, and when they are added to get the battery current, so the total output current is like this. See, it is a 3 means simulation as well as the hardware result. Similarly, some of the winding current and voltages we have shown here. These are some for sensor reductions we are trying to test. Okay. Again, if we have a 6-phase machine, a 6-phase multi-phase converter, let's say all the 4-wheel drive system where the rear wheel infrastructure is used to convert AC into DC, then we required a 6 leg is there, 2 motor winding make 6 windings, and then we required a 6 sensors. So they are very costly affair. So instead of putting 6 sensor, you can use 1 sensor at the DC link, like we have right side of the diagram, and this will help us to operate the whole system in the similar way as we done for the AC to DC converter. So for this case, we have also implemented the same thing, and it is working fine in system simulation as well as the hardware result. Now I have also make let's say the 2 vehicle running. So why not we use different operations like vehicle to grid to vehicle operations, and then vehicle to vehicle operation. So if you see the figure B, lower figure of this, the first figure is related to the first vehicle, but the second figure, lower figure, is related to 2 vehicle transferring power to each other. So in this configuration, the vehicle 1 is allowed to charge the battery by vehicle to grid to vehicle operation, or it can pump the power from battery to a grid, so it is a vehicle to grid operation. Similarly, the vehicle 2 is of same nature. It can charge through the G to V, or it can pump power from battery to vehicle. But in some places, let's say some remote area where grid is not available and where one vehicle is a drain, so you can allow charge from vehicle to vehicle. So you can use the DC link of both as I shown with the red color, and it can be used to charge one vehicle to other through the V to V operation, vehicle to vehicle operation. So this work is also carried out by one of my research scholar, and then all the associated control for vehicle to grid, grid to vehicle, and then V to V. These all 3 control are implemented. Their corresponding waveforms are shown. It is very difficult for this much time we have to explain all this, but this topology is working fine. So this is all from my side. If you have anything to ask, I'm open.
Thank you, sir, for your remarkable lecture. Your ability to simplify complex idea and inspire critical thinking is truly commendable. We deeply appreciate your valuable contribution. Now I request to participant, please ask the question, and you can also write in chat box.
I'll be more happy if some of the person, those who are working in this area, and they can ask question. Even if they have a problem related to their research, it is. Yes, please, anyone? So anyone can ask questions. Hello.
I think there is no question.
Okay. No. So if there is no question.
If anyone want to ask, please ask. Unmute yourself and ask question to sir.
No, ma'am. No question.
Okay.
So, so thank you all.
Thank you, sir.
Thank you, sir.
Thank you, Rakesh sir. Dr.
So,
Nodeep.
okay, Navdeep ji, so if you allow, can I leave?
Yes,
May I
sir.
leave?
It is. Hello,
Hello, yes, I'm
Rakesh
audible.
sir.
Yes, sir.
Yeah, yeah. Is it any query? Maybe there is no query, sir. Thank you, sir. One question maybe is came from Sumendra Banerjee.
Yes, yes, sir. Can we use bidirectional converter for feeding EV in place of DEF converter? Yes, yes, of course. See, I have given two topology where the DC to DC side, rear wheel side, you can configure either multi-phase DC to DC, multi-phase buck converter, so that can be operated either boost mode as well as the buck mode. So whenever, let's say when you are feeding power to charge your battery, then obviously it will be work as a buck mode. But when your battery is going to feed power to grid through this DC to DC converter, so the same converter will be operated in the boost mode also. So not necessary you use a DAP converter. You can use a conventional buck converter also. But idea is to utilize, because when you add a DAP converter, obviously you require larger switching frequency, and then you can incorporate the feature of zero voltage switching, zero current switching in order to make it more efficient. Okay. So I hope.
Yeah, sir. Maybe all query has been clear.
Okay. So thank you all. Thank you for
Thank you,
patience
sir,
hearing.
for this informative lecture. Thank you, sir.
Thank you. Thank you. So now I'm leaving now. Okay.
Yes, sir. Yes, sir. You can.
So shall I start
Sanjeev sir,
routine session?
help. Nikita, wait. Sanjeev sir is there or not?
Okay, sir. Sir, um,
Sanjeev sir?
I think
Sir, he is not added right now.
yes, sir.
Okay, I will put a message because he is living in a US.
Okay, sir.
So I put a message at that time. It will take 5 to 6 minutes. After that time, it will be added. Nikita,
Yes, sir. Okay, sir.
wait for a 5 minute. After that time, he will be added.